Hello, physics friends, and welcome to Chapter 4, which is entitled Forces, specifically forces in one dimension. So we've been talking about position, velocity, and acceleration, and now we're going to bring force into it. And a force is a push or a pull. When you push on an object, how does that affect the object's acceleration? How does that affect the object's velocity? And how does it affect an object's position? So we're just going to go one more step up the rung in bringing force into this. Now, the definition of force is a push or a pull. It's a push or pull an object. Now, how you push or pull on an object is very important, meaning it's a vector quantity. Like if you push down or if you push left or you push right, it is a vector quantity. The direction matters. Now, your book defines forces. It says that there are two types of forces: a contact force, where you physically touch something, and a non-contact force like gravity or magnetism. That's not true. That's not the way the scientific community currently lumps forces. It knows of four forces right now, and it's understanding. We currently understand four forces. The first one is gravity. The second force is magnetism, more specifically electromagnetism. Now, either of these, gravity is like a pull. It's a physical attraction between two masses. Electromagnetism, like two charged particles like electrons repel one another. Two positive particles push against one another. The third one is the strong nuclear force. The strong nuclear force is responsible for keeping a nucleus together. There's a force that keeps those things bound. And then lastly is the weak nuclear. The weak nuclear force is responsible for radioactive decay. We'll get into more of that, all of these, if you want. I'll put some links down here so you can, if you want to know a little bit more about them, I'll show you a little bit more about them. The first thing that we're going to have to know how to do when we deal with forces is draw pictures. Now, we do what are called free body diagrams. A free body diagram is drawing a picture and labeling the forces on that picture. And we always label forces with an arrow. So I'm going to do 4 examples here. It says draw a free body diagram for each of these 4 scenarios. The first one says a flower pot falls freely. Ignore air resistance. So what we're going to do for number 1, we're going to draw a flower pot. And this flower pot is falling freely. So what we're going to do is draw the forces. Now, in I think every single case we have, there's always a one force that you can never escape, and that's gravity. Gravity always points towards the center of the earth. Now, because there's no air resistance, there's no up force. So this is the only force that's acting on this flower pot right now. Number 2 says a skydiver falling downward through air. So again, this person probably weighs more than the flower pot. So I'm going to draw this arrow longer just to represent a larger force. The air exerts an upward force on the person. Now there's something here, constant velocity. You haven't been introduced to this yet, but whenever something's moving at a constant velocity, that means that the forces are balanced and equal. So there's air resistant force is equal and opposite. I'll explain more about that as we go. Number 3, a cable pulls a crate at a constant speed. So here's my box or my crate. Again, I still have gravity. There's always gravity in all of these. Now, there's a supporting force that prevents the box from going towards the center of the earth provided by the surface. We call this the normal force. I'm pulling it, so I don't know how big my pull is. But you'll notice that there's probably friction. It says the surface provides a force that resists it. And again, it says constant speed. So friction is here that's equal and opposite the force of the pull. Number 4, a rope lifts a bucket. So here's my bucket. And I've got a rope lifting it. So I'll just say the force of my pull. What we do, these are called subscripts. I use a big F to represent a force, and then what's providing that, or the agent of that force, I put in the subscript below it, like pull force. And we're lifting at a constant speed. So again, we've got gravity down here. And gravity is the same size and equal as the pull. Now, when you do your free body diagrams, remember, your arrows always come from your object. You might think that gravity pushes you down and you have the arrow going at the person. That would be incorrect. We always draw it from our object. When we've got multiple forces acting on an object, here's a bunch of kids pulling on a rope, we have what a net force. The net force is the sum total of all forces acting on a body. So in this last case here, the sum total force of all, let's just pretend this flower pot weighed 5 pounds. The net force here is 5 pounds. That's the total force. Let's say this person's 180 pounds. So that means the air resistance is the equal and opposite, so the net force here is 0. Because they're equal and opposite, they're canceling each other out. Same with this crate. Gravity equals the normal, the pull equals the force of friction, so the net force in this case is also 0. And the same way in this last one, it's 0. Now, there's a special thing that happens if the net force is 0. We call it equilibrium. If something is in equilibrium, just like its name implies, the forces are equal and opposite. Now, here's an example. What is the net force on each of the situations below? You're pulling to the right at 100 and left at 100. The net force is 0. You're pulling to the right at 100 and the right at another 100. The net force is 200 newtons to the right. You have to make sure that you're denoting a direction with these because a force is a vector. It's a magnitude and direction. So here, the net force is 100 newtons to the left. Isaac Newton. And you'll notice I've been using these numbers right here, or this unit, and you probably haven't never heard of this before. A Newton is actually a unit of force, and it was named after Sir Isaac Newton. Isaac Newton was probably the single greatest contributor to our physics understanding in the history of mankind. He invented calculus. He found out that light is a wave, and he also figured out the laws in which gravity are formed. And he came up, there are 3 laws which he derived. And his first law is that an object in motion stays in motion. In a straight line. Unless acted upon by a force. On Earth, if I let go of something, I could push it forward, and it's not gonna follow a straight line because the force of gravity is acting upon it. Einstein went further than that. He said that actually it is riding on a straight line. It's riding on a straight line that is curved space-time. So Einstein improved upon Isaac Newton's ideas, but we're going to stick to Isaac Newton's ideas because it works pretty well for us right now. I'm going to give you a cool little example of this. Up on the International Space Station, you can throw things in a perfectly straight line because there's microgravity up there. He's going to let go of this baseball, and you're going to see it moves in a perfectly straight line, not being affected by gravity. And he's going to hit it with his flashlight, moves again in a straight line, he goes up, grabs it. Objects in motion stay in motion in a straight line unless acted upon by a force. Newton's second law says this. I'm going to write it very simply. F equals ma. Force equals mass times acceleration. And force, we label it in newtons. Mass is in kilograms. And acceleration is in meters per second squared. Here's what it says in words. It says this. If you have a big force, that means you have a big acceleration. Your acceleration is directly proportional to your force. So a big force equals a big acceleration. A small force equals a small acceleration, if the mass stays the same. If we alter the mass, if we keep the same force but we've got something more massive, a larger mass, if your mass goes up, your acceleration goes down. They're indirectly proportional. Let me show you an example of that. This is an astronaut in the European Space Station, European Space Agency, up on the space station. He's got 3 different spheres that he lets go of, and then he's going to blow on them to give them all the exact same force and to see what happens. It's actually pretty neat. So what he's got here, he's got a ping pong ball, a wooden ball, and a brass ball. And it's funny, they took them up to the space station for this only demonstration. Like they paid that to get that up there just for this demonstration. It's really cool.
We're adding a ping pong ball.
You see that? He exerted the same force on all of them. He blew on them. And the one that's lighter, because it has a lighter mass, it's got a bigger acceleration. The thing that has the biggest mass has the smallest acceleration. That's what we call inversely proportional.
We're adding a ping pong ball.
And then lastly, Newton's third law. Newton's third law says this: for every action, there is an equal and opposite reaction. For every action force, there's an equal and opposite reaction force. And let me give you an example here. I've got one final little video demo to show you. With this is at MIT. They're using a tricycle that they outfitted with a fire extinguisher on it. So you can see here that there's... I'll just let it play out here. There's a force acting on this. They're pushing some material this way with some force. And there's an equal and opposite reaction force pushing it the other way. So there's some force there, and there's an equal and opposite reactive force pushing it the other way. And this force is actually what accelerates him. So the forces are the same, but because this person's mass is so large, he's got a very small acceleration. Because the mass is so small, it's got a very large acceleration. This gas is flying out of here, but this guy just barely inches forward because of their masses. Their acceleration is directly in proportional to their mass. Big mass, small acceleration, but the same force. We'll investigate this more in sections to come. The last thing I wanted to talk about today, here's a list of some of the forces that you're going to see. Friction, it always opposes motion. The normal force is we talked about, it's a supporting force. It's always perpendicular to a surface. So if you've got a flat surface, the normal force points straight up. If you've got an inclined plane, that means the normal force is acting at an angle, but it's always at a right angle to the surface. A spring force is a restoring force. It's opposite the displacement. So if you pull a spring down, it wants to pull it back up. If you push a spring up, it wants to push it down. It's always going against the displacement. Tension is provided by a rope. It's always in the direction of a rope. Thrust is like rockets. It's in the same direction as the accelerating object. And then weight. Weight is always straight down towards the center of the earth. And that's what I want to talk about last for today, is the difference between mass and weight. We measure mass in kilograms. Weight is a force. Up on the International Space Station, you don't have any weight. You're weightless. But you still have mass. You saw that those metal ball and the ping pong ball, they still accelerated proportional to their mass, in to their mass. So mass is a scalar quantity. It doesn't need a direction. Weight is a vector quantity. It's always pointing down towards the center of the earth. We measure force in newtons. One newton is approximately, let's see here, I think there's 2.2 pounds in 1 newton. So that's roughly. And it turns out that 1 newton equals 1 kilogram meter per second squared. And if you think about it, remember how I told you before F equals ma? Remember how mass is kilograms and acceleration is meters per second squared? There you have it, kilogram meter per second squared. So instead of writing that every time, we just write it as 1 newton. Your mass is the same everywhere. One kilogram on Earth is equal to 1 kilogram on Moon, which is equal to 1 kilogram in the middle of deep space. Your weight depends. It depends where you are. It depends where you are on planet Earth. Planet Earth's gravity is not the same everywhere. It depends on what planet are you on. Are you on the Moon? Are you on Mars? Are you on Earth? Are you in space? Weight is different. Weight depends. Now, to switch between weight and mass, there's a really simple conversion. We're so used to in our daily lives using the words weight and mass interchangeably. It's like using speed and velocity. You probably use those words all the time, and they mean the same thing to you. But in physics class, speed and velocity are different. In physics class, mass and weight are also different. Mass and weight, you can change between the two by this equation. F equals ma. Your mass goes in here, your weight goes in here, because it's a force, and the acceleration is always 9.80 meters per second squared. Let me give you an example. 1 kilogram, that's a mass. 1 kilogram times 9.80, 1 kilogram equals 9.80 newtons. Like that. 1 newton, I put a 1 over here, and acceleration still equals 9.80. I wonder what its mass is. 1 divided by 9.80. .102. 1 newton equals 0.102 kilograms. So if you want to go from one to the other, what you do is you run it through this equation, F equals ma. If you know the mass, put it in for m, multiply it by 9.8, and you'll get out what it weighs in newtons. If you know what it weighs in newtons, divide by 9.8 to get what it is, its mass.